All right, we're on the back of the notes right now, starting on number 16. Magnetic fields and electrostatic fields, when these things start to interact, everything gets three-dimensional. So we have to draw three-dimensional symbols. We understand using arrows to go left, right, up, and down. We've done that for a long time, but now three-dimensionally, there's going to be a Z dimension, which is going to include things going into our page, into the page in front of you or the screen in front of you, and as well as out of the page. The best way to remember these is imagine that you're shooting an arrow. If you're shooting an arrow into the page in front of you, what you see is the back of the arrow, the cross of the, maybe the feathers of the arrow, you might imagine. If you see an arrow coming toward you, coming out of the page toward you, all you see is the point of the arrow there, which would indicate the dot. All right, so this is three-dimensional stuff. And we're going to skip 17 and we're going to go to 18. 18 goes directly to the three-dimensionality of this stuff. 18 talks about the right-hand rule. This is the first right-hand rule. There's actually 3 right-hand rules, but we're only going to talk about 2 in this class. This right-hand rule is to talk about the direction of a magnetic field in a wire. As I said, the basic thing about a magnetic field is that all you have to do is move an electric current. Well, that's what a wire is designed to do. A wire is designed to move electric current through here. So since we move electric current through a wire, that means that a wire is going to be temporarily magnetized. So if I look at a wire like this, wires are made of copper, and copper is not on that list of permanently magnetizable materials. And as you see, as I wave this wire over the compass, nothing happens because the wire is not magnetic, and I cannot get the wire to respond to this magnet here. All right? But if I run current through this, then I can create a magnetic field. And we need to know the direction of that magnetic field. So the way to do that is just take your pencil or pen, whatever you're writing with right now, and I want you to grab it with your left hand like this. And if you do that to where your thumb is pointing in the direction that the pen is pointing, imagine right now that you're actually holding a wire instead of your pen. You're holding a wire and your thumb is pointing in the direction of current. And if that's true, if the current is running in the direction of my thumb, and I hold the wire like this, my fingers actually now give me the direction of the magnetic field. The magnetic field is not linear in a wire. The magnetic field in a wire actually goes in a circle, you get a circle, around the wire. So the magnetic field goes like this around the wire, comes out this way, so it's going like this around and around the wire. That's what the magnetic field in a wire looks like. That is the first right-hand rule. So in this right-hand rule, the thumb represents the direction of current flow as is shown here. You wrap your fingers around your pen or whatever it is as if you're grabbing a wire, and if you do that, your fingers are now showing you the circular direction of the magnetic field. As you can see in this picture, this magnetic field in this wire is going into the page at the top, and then it comes back around and comes back out of the page at the bottom. It's a circular magnetic field around that wire. When we measure magnetic fields, the unit that we use to measure magnetic field is called the Tesla. That's named after Nikola Tesla. We can have a big, long, interesting discussion about Nikola Tesla and his fights with Thomas Edison, but we won't do that right now. Just know that we honor him with this unit. All right, I want you to cross out number 20 and number 21. Those are fairly redundant. I'm going to go straight to 22, which is this equation here, F equals QVB. This is number 35 in your equation chart. And this tells us about the force on a charge that is shot through a magnetic field. Go ahead and write this down in your notes, and then I'm going to explain what I mean by this equation. Q is charge, V is velocity, B is a magnetic field of this equation. Let me show you what I mean by this. Here's what this equation is saying. Remember, we talked about all we have to do is simply move an electric charge to create a magnetic field. And that's as simple as shooting an electron. Right? That's a moving electric charge, which means there's going to be a magnetic field set up in this direction. That's a temporary magnetic field, but it's a magnetic field just the same, which can respond to another magnetic field that is set up within a permanent north-south magnet. So when we do this, we can look at the charge of this electrically charged particle, we can look at the velocity of that particle, and we can look at the magnetic field strength of this magnet. And all of those put together can tell us the force felt by this particle because of these two interacting magnetic fields. That's what this equation is all about. This equation only gives us the magnitude of that force, though. We're going to do the third right-hand rule to look at the direction of the force. Number 23, the other equation you need to know is this one. This is how to find the force on a current carrying wire, F equals ILB. This is equation number 36 in your chart. I we've had before, that's the current in the wire. L is the length of the wire in meters. And again, B is the magnetic field strength in Tesla. It's simply another equation that you simply plug numbers into. Gives us the force created by a current carrying wire. Once you get through writing that down, you can cross out number 24. That tells us more about solenoid type stuff, and we don't really need to know about solenoids in this class. We're going to go straight to 25, which is the right-hand rule. All right, this is the third right-hand rule. We skipped the second one. The third right-hand rule helps us to determine the direction of the magnetic force, right? And let me just set up the scenario before you write anything down. Down here in the bottom right-hand corner is the scenario we're dealing with. Remember this symbol means into the page. Imagine that this symbol represents an electric charge, an electron, let's say, that is shot in a straight line into the page. So imagine that you've got an electron gun and you've shot this electron in this direction into the page. This electron is traveling in a straight line in between two permanent magnets, the north end of one and the south end of another. And if you remember that the magnetic fields always go from north to south, so the magnetic field that this electron is traveling through goes to the left, from the north to the south, from the north to the south. So we have an electron traveling into the page through a leftward directed electric field. Remember, there are two magnetic fields here now that are going to be existing because this moving electric charge is going to create its own magnetic field. Those magnetic fields are going to interact with each other, and this charge is going to feel a force from the magnetic field set up between these two magnets. We want to know the direction of that force, and that's what the third right-hand rule is all about. The third right-hand rule uses your three fingers. All you have to do is you get your gun first, and then you simply take your middle finger and you move it out like this. And so your hand needs to be in this configuration, and it cannot change. You can't move your fingers around like this. You can't do anything like that. You can't move your thumb. This isn't thumb war. This is the third right-hand rule. Okay, and so what you need to write down on your notes there is that your thumb is going to represent the force felt by that traveling charged particle. You can think about maybe thumb wars. Your thumb is your strongest finger, so your thumb represents force. Your index finger, or your pointer finger, your forefinger, represents the velocity or the current. Really, it represents the direction of the motion of the charged particle. All right. In the case in the screen that we looked at before, that would be into the page. And then your middle finger represents the direction of the magnetic field. So this is a three-dimensional situation here that we're going to need to analyze. So here was our situation. Remember that we had a particle traveling into the page, into our screen in front of us, and it was traveling through another magnetic field that went from right to left. The magnetic field goes north to south. So this is the direction of motion of the particle, or the current, the I, that goes into the page. Here's how we do the right-hand rule. All you have to do in each one of these problems, you're going to be given two of the three directions given by your three fingers. All you have to do is pick one of those two, and then you make your hand orient to where the second of the two matches, and then the third is given. Here's what I mean by that. I know the direction of the B, which is my middle finger, and I know the direction of the current, or the velocity of the particle, which is represented by my forefinger. I'm just going to start with the velocity of the particle, and I'm going to make my forefinger go in that direction, which is into the screen or into the board. I can't move that forefinger now. If you notice, imagine that you put your forefinger in a hole, and I can move it around, I can rotate around that forefinger to where the direction of this one doesn't change, but the other ones do. And that's what I'm going to do here. I'm going to put it in there because I know that's the direction of this particle. And I'm not going to move my forefinger, but I can rotate these to where they can change. And I need to do that because I need to rotate them until the second direction that I know matches. The second direction that I know is the magnetic field. That's represented by your middle finger. So keeping your index finger where it is, you would rotate your hand until your middle finger matches the direction of the magnetic field. Maybe I should do it this way. matches the direction of the magnetic field, which is going to the left. So the magnetic field, my middle finger is pointing to the left in the direction of the magnetic field. My index finger is still pointing into the board, which is the way it should be. And if my hand is oriented in this way, and those two directions are matched by my hand, I now have the third direction given by my third finger, which in this case is my thumb. My thumb is pointing upward, so that tells me that the force felt by this particle would be upward. It would be deflected upward. All that to say, if you shoot an electrically charged particle through this magnetic field, it will feel a force upward. Now, I'll tell you this. This is only true for electrons, for negatively charged particles. If the particle has a positive charge, all this gets reversed. But we're not going to talk about that reversal in this class. All you really need to know is how to do this with negative charges, and that's all we're going to have. Reversing, that's a little bit more advanced. I'm just concerned about that you know how to figure this out three-dimensionally. Okay, let's look at another one. Let's just imagine that we've got, let's say, the magnetic field goes to the left again, and let's say that we know the force is going into the page, let's say, right? And we want to know the direction of the current, the direction that the charged particle is moving. This is the last one I'll do. Once again, let's just pick one. We know B and we know F. B is represented by the middle finger, F by the thumb. Let's just do the thumb. My thumb needs to go into the board, into the screen. So that's what I'm going to do right now. Okay, it goes in there. Again, I can rotate around the thumb. The thumb stays in the same direction, but the other two can change. And they need to change because I need to make the middle finger, my B, match the direction of this B. And you may need to do a little bit of contortion to do this, but I'm going to rotate around until my thumb's still pointing into the board. I'm going to rotate around until, I rotated too far actually. My B, my middle finger, is now pointing up. I'm going to rotate around until my middle finger is pointing in the direction of the B, that's to the left. And now that gives me the direction of the motion of the particle. My forefinger particle would be moving down. Let's look at another one. Let's say the force is to the left and the magnetic field, let's see, force is to the left, and let's say the magnetic field would be up. All right, if force is to the left, that would be your thumb. Thumb has to start out going to the left, and I can rotate around the thumb and it stays the same direction, and I want to make the other two match. It just so happens if you're in this configuration, it happens to match because the magnetic field is your middle finger, it goes up, and now the direction of the particle is given. If you look at your index finger, my index finger is pointing into the board once these other two match. So that tells me that the current, the motion of the particle is into the board. It's going into the screen in front of me. That's basically how the third right-hand rule works.